Okay. So my name is Maxime Rossibelon, and together with my colleague Damiano Melotti, we are going to speak about the Titan M chip and how we perform vulnerability research on it. And you may have noticed that nowadays, smartphone vendors tend to integrate hardware security modules in their smartphones, and on this module relies the most critical security features of the device. And these modules come with cryptographic capabilities and hardware protections against hardware reverse engineering or fault injection. And most of their design is both hardware and software is only known by the chip manufacturer, or sometimes the vendor. Yet for us, security researchers, these components are a key in the whole device security, which is pretty much the motivation for this talk today. We will show you how we performed the vulnerability research on the Titan M chip, so a security chip designed by Google for their Pixel devices. And we hope that what we will show you today will be useful to other researchers who will face similar targets. So we are both security researchers at Quarks Lab, and we are working in a team that deals with embedded devices, embedded targets, and we're also very curious about mobile targets. Now, we are going to speak about the Titan M chip. So it's, in fact, yesterday there were this great talk about some folks at Google about how they red teamed the Titan M2 device. So the Titan device we are speaking about today is the old generation one. And on this device, it has been introduced, in fact, starting from the Pixel 3 and up to the Pixel 5, I guess. And on this device, you will realize the critical security features of the smartphone. And among them, you will find the secure boot. You will find the unlock feature using the PIN code or the password, and also the key store, which is probably the most important one for us today. This feature allows Android applications to generate and use keys from within a safe environment, meaning the Titan M chip. And whenever this feature relies on a security chip, it is called Strongbox. Now, it is important to keep in mind that this chip is separated from the main CPU, from the application processor. You have one hand the main system on chip that runs Android and its application, and you have another chip, the Titan M chip, that communicates together through an hardware bus as a client-server model. Now, according to Google, this chip has been introduced in order to mitigate a wide range of side-channel attacks that were impacting the ARM trust zone, where previously the features I mentioned were implemented into. Now, this Titan M is based on ARM Cortex-M3 architecture, which is quite common for microcontrollers. The firmware is closed source, but it is based on an open source OS called EC. EC stands for Embedded Controller, and it's designed by Google, and it targets the various microcontrollers of the Chrome OS project, which is why it's quite simple and small. For example, there is pretty much no dynamic allocation in it. And most of the code is running into tasks that can be compared to applications in bigger OSs. Now, the two hardware buses that are interesting for us today are, first of all, the SPI bus that is used to communicate with the application processor and with Android, and the UART bus that is not available by default, but we will show you how you can find it on some devices. And the UART is used for the logs and a minimalistic console. Now let's zoom into the way Android communicates with the Titan M. So you have the SPI bus, and on the main CPU, you have a kernel driver that will handle the SPI communication, and it exposes an IOCTL interface to the daemons. And in fact, you have only one daemon on Android that communicates with this driver. It's called citadld, and its role is to dispatch the various messages received from services to the driver. Now, these services, I call them here HAL for hardware abstraction layer. There is one service per functionality, so one for key store, one for wither. And this service will translate the generic Android API into something custom. And here, to do so, they use Protobuf, a famous serialization framework designed by Google. And thanks for us, in fact, the definitions, the protobuf definitions are available in the IOSP repository. So it will be quite convenient for the different tools that we'll present today. It is not the first time we speak about the Titan chip. In fact, last year at Black Hat Europe, we presented the first stages of our research on this chip, and it can be summarized as the following. So the first thing we did was to reverse the firmware. We identified the firmware file, and the next thing was to, in order to help us in this reverse step, we wanted to interact with the chip. And first of all, on Android, we implemented a Frida script in order to sniff all the communications going on. So we hooked the Citadel daemon, and thanks to that, we were able to see all the messages sent by the applications. And we also implemented our tool that we call Nose Clients in order to send custom commands to the chip. Now, our tools only run on Android, but there are some commands that are exchanged with the chip that are sent to the chip, by the bootloader of the main CPU. And in order to see what's going on, we wanted to do the same things on the hardware level. And this is the picture you see on the left. It's probably the most impressive thing that we presented, at least visually, last year, thanks to the magic hands of our colleague, Philippe Dewan. He was able to solder each of the 64 pins of the chip onto a breakout board and then back to the footprint on the smartphones. And thanks to that, we were able to interact with the chip from the hardware level. The next thing we did was to find vulnerabilities, and the most important one was a downgrade issue that allowed us to flash any old firmware. And with the side effect that all the data would be erased from the chip. Now, using this vulnerability, we have been able to downgrade into an old firmware on which we discovered we identified a one-day vulnerability that we then exploited, and it allowed us to execute code on the chip, and in the end, to leak various hidden parts of the firmware, including the boot ROM. Now, today, we are going to speak about fuzzing and how useful it can be on this target, even though it's quite constrained. There is no, we don't have the sources. There are a lot of hardware interactions, but we can get interesting results. So we will cover two approaches. First of all, the black box fuzzing. In that case, we don't have any idea of what's going on inside the chip. And we will also cover the emulation-based fuzzing, where we have a lot more insight of what's going on, yet we will show you a few tricks to optimize the results. So the next thing is that we will show you how we exploited, without any debuggers or stack traces, a vulnerability that we discovered, and how, thanks to this vulnerability, we have been able to execute code on the chip and to compromise one of the most important security property behind that chip. So I'm now going to let Damiano speak about the black box fuzzing.
Okay, so when starting to test a chip like the Titan M, one of the first steps that one can try to make is start with black box fuzzing. And here by black box, we mean when we only have very limited visibility on the target that we want to test. All we need actually is just a channel to send messages to this target, and then a signal that tells us what happened. So in our case, this was given by the custom clients that we developed to communicate with the chip. We could send arbitrary messages that we could mutate in the fuzzing workflow, and then get a return code back that would tell us what is the result of the processing of our message. Now, the return codes are also in the AOSP, and you can see them on this slide. Generally, we are interested in those return codes higher than or equal to, with 2 being error internal. This is, for example, the one we get when the chip crashes. So we just implement this by plugging a mutator into our NOS client. The mutator is libprotobuf mutator because we leverage the grammar that is available. It is actually fairly straightforward to use. We start from an empty corpus, but we do try to set some fields that would make us pass certain checks to make sure that we can explore more states. And then, of course, we keep the inputs that generate some interesting return codes. Now, we did a first campaign on an old version of the firmware, a firmware we knew had some vulnerabilities, and we managed to discover a bunch of them. One of them is actually the buffer overflow that we had exploited by rolling back the firmware. So this kind of told us that the approach was working, and we repeated the same procedure with the latest firmware at the time. We found two commands that were leading to a null pointer dereference that was making the chip crash. So we reported this vulnerability like the others, and this one was not considered serious enough to end up in the security bulletin. The interesting part is that all these results come after just a few minutes of fuzzing. So this is kind of suggesting that the approach is working. We get the bugs, so that's positive. It is also, as I said, fairly easy to put in place, and we are testing in the real device. So what we get is going to be reproducible for sure. But at the same time, there is a very well-known limitation when it comes to black box fuzzing. That is that we are probably only exercising the shallow states of the targets. We also are prone to false positive with this return code heuristics that we implemented. And detection is quite complicated. We only detect those bugs that produce a meaningful return code, which is not always the case. So the bottom line is really that it is hard to know what is going on the target. So that is when we wanted to move forward and try to explore a different approach that is emulation-based fuzzing. And this comes from the fact that we know how the firmware works. We have been reversing it, and we know also how to leak some parts of the memory when we need to do so, thanks to the vulnerability we exploited by rolling back the firmware. So we can put this together and emulate the firmware on our laptop. This way we control what is being executed, and we also have a very good feedback for a fuzzer if we want to do coverage-guided fuzzing. So to emulate the firmware, we have, of course, many different frameworks out there. In the end, we decided to use Unicorn. This is a framework that is built on top of QEMU, and it allows to emulate only the CPU without caring about full system emulation, which is something we actually wanted. So we can actually set it up fairly easily and tweak it to try to detect more bugs. And also a very interesting feature of Unicorn is that it integrates very well with AFL++. And I'm sure most of the audience will be familiar with it. AFL++ has this Unicorn mode that basically allows you to fuzz anything that you can emulate with Unicorn. You only need to take care about writing your input somewhere in the memory of your emulation script. And then you will get the classical AFL experience that is also allowing, for example, to use custom mutators, which is something we used extensively. Another nice property about emulation-based fuzzing is that you can fuzz anything you want. All you need is an entry point, some properties that you want to set, such as the value of the registers and the memory mappings, and then a point where you want to exit your execution. So this gives a lot of freedom. At the same time, we, of course, need to take into account that we want to keep it consistent with the surface that an attacker is actually able to reach. But one attack surface that is exposed that we hadn't explored earlier is the SPI rescue feature. So this is a feature that allows to flash a new firmware by sending a new firmware in this specific format that you see on the slide. This is done through the bootloader, and the user data on the chip are going to be wiped. So since this is a fairly interesting format, we wanted to check whether this was actually processed correctly. So we fuzzed the handler of this feature on the firmware. And the way we did it was using, as I anticipated, a custom mutator. We used Format Fuzzer in this case. There is a project that allows to generate and parse binary files following a specific format, and that runs with a modified version of AFL. Now, unfortunately, we couldn't really find any interesting bugs in this campaign. But still, having to build an emulation script for this feature kind of got us to a next level of reverse engineering, and we discovered some things that at least myself, I wasn't able to understand with simple static reversing. When you need to sort out how to make it work, you kind of get a little bit further. So one example is that the bytes in the hash, the 0 bytes get replaced with 1. And this is something that was just interesting to discover in the process. But then we wanted to go back to the tasks. So repeat the same campaign, but using emulation this time. So again, we base ourselves on libprotobuf mutator, and we focus mostly on 3 tasks. Actually 2, identity and key master. There's also Weaver, but it is fairly simple, and there isn't really much to explore there, at least from a fuzzing perspective. So the first question is, can we actually find the same bugs we know about? Otherwise, we're not really making any progress. And the answer is yes, but apart from one, which will actually bring me to the limitations of this approach. Because as we know, there is never a free lunch. In this case, emulation has always the problem of hardware-dependent code that you really don't know how to emulate. The way we did it was just hooking those functions that we knew were not possible to actually emulate. Also in this case, detection is still not perfect because we only detect a bug when unicorn crashes. But if there is an off by one or a corruption in a page that is already mapped, we're not really able to detect that. And then no full system emulation. This was our choice. But of course, no full system emulation, you don't get those bugs that entail for example, the scheduler. This is the reason why we didn't manage to find again that one bug that I mentioned. But really what is nice about this approach is that you can tweak it a lot. You can come up with heuristics and hooks that try to look for specific patterns of things that you know are not supposed to happen. We have been, for example, checking for mem copies that end up reading from the boot ROM that is mapped at the address 0. This was a pattern for some bugs that we kind of wanted to double check, and this was possible with a custom hook. But at some point, there is a trade-off between how much you reverse engineer and come up with these tweaks and how much you finally let your fuzzer run. But what we are presenting today is also one specific vulnerability that we found. And this is a vulnerability in a function called param_find_digest internal. This is a function that parses key parameter objects inside requests. And specifically, this is an out-of-bounds write of exactly 1 byte that is set to exactly 1. So the first time I bumped into this, I thought, okay, this is probably a minor issue, no way to exploit it. But let me walk you through it. So here you see the assembly and decompiled view of the function. And this is the vulnerable instruction, store byte, so 1 byte instruction. But there are some checks, actually a lot of checks on the offset. So let's start from a 32-bit value. Actually, we only care about the least significant byte because of a mask that is applied. This is actually interesting for us. But that 1 byte has to go through a lot of checks. So first of all, it needs to be smaller than or equal 4. So we kind of lose all those bits. And then there is a little bit of a complicated bitwise operation, which just bear with me for now. If we put everything together, the least significant byte can only be 0, 2, or 4 out of the 255 possible values. So what can we do? There are actually multiple ways to get to this snippet of code. As I told you, it's a function that processes this type of field in different messages. And also, don't forget that TitanM has a static memory layout. Objects are always at the same place. So if we can write that 1 byte at the right place, we might be able to get something interesting, you know, from a simple denial of service to perhaps changing some field that gives us a corruption elsewhere. There is a lot that we can do. So what we did was we generated all the possible addresses we could reach, and then we tried to look one by one and see what we could do with them. And we arrive at a point where we understood that there was this structure in memory. We called it keymaster SPI data, and we could overwrite 1 byte in a field that we called request address, command request address. So this is a structure that is meant to hold data about SPI exchanges for the keymaster task. Specifically, there's one for each task. And the actual field that we are overwriting is the one that is expressing the address where keymaster messages will end up being stored. So as you can see, from 192C8, we go to 101C8. So now requests will be stored quite far from where they're supposed to be. And this was the beginning of the fun part. But first, don't forget that all we have to communicate with this TitanM chip is our NOS client. So all we can do is force the message the way we like it, send it through our binary, and then get a return code. Perhaps return code 2 if the chip crashes, but not much. So as you can imagine, developing and debugging an exploit is quite of a challenge. But there's an ace we have been keeping in our holes so far. Max briefly mentioned this UART that we could access. And this is specifically thanks to 2 pins that are exposed on the motherboard. So we soldered 2 wires into those pins, and we ended up getting this UART console that is actually fairly simple, and you cannot really do much apart from asking to the chip about versions and statistics and stuff like that. But it is the place where the logs of the chip are printed. So although this doesn't provide any information on what goes wrong when something doesn't work, this is very useful when writing an exploit, because we can always try to trigger some logs and see if we can actually get them on the UART. So I'm not gonna go, sadly there's no time to go over the memory layout of the TitanM chip, so we just want to write our requests to the new address and basically see what happens. So we send bigger and bigger payloads while monitoring the UART, okay? So we send bigger and payloads, and at some point we realize that the chip starts crashing. So what if we place actually a function that logs the tasks right at this point where the chip starts crashing, and what we get is actually the logs on the UART that tells us that we are triggering a function, we are getting code execution. So what's going on? Probably this is, our guess at least, is that this is an address that was pushed into the stack by some task that is maybe has to return there after its execution. And from now on, things get quite complex to actually get an exploit working. We need to move elsewhere because we cannot write any ROP chain there. It's quite cumbersome, but we are actually releasing a blog post where we go over also the exploitation details of this vulnerability. But now I'm going to hand it over to Max for the impact that we achieved.
Thank you, Damiano. So let's look at the impact of this vulnerability, not only on the chip itself, but on the whole system security. Something that would be great for us would be to find a memory region that is both writable and executable, so we can write on our code. But there is no such region. So another thing we could try would be to reconfigure this memory and permissions by playing with something called the MPUs for memory protection unit. But on TitanM, this MPU has a custom interface that we did not spend enough time to reverse it. So what we can do is to reuse the code that is already present in the firmware, like making ROP chains like Damiano explained. And doing so, we implemented again a leak command in our NOS client tool, this time based on the 0-day we just presented. So since we did not downgraded the firmware this time, the data is not erased, meaning that we can leak all the secrets present in the chip's memory. And the command you see below, the leak command, so is the one I'm speaking about. Here we are leaking this first 16 bytes that are present at the address 0, and at the address 0, you have the boot ROM, so you see the first bytes of the boot ROM. But can we do something more harmful with this vulnerability, more harmful on the device? Can we leak strongbox keys? But before I answer that question, let's first have a look at what is Strongbox. So it's the hardware-backed version of the key store, and it allows applications to generate and use keys from within a safe environment, meaning the Titan M chip. But the Titan M does not store any keys. Instead, the keys are stored in objects called key blobs that are encrypted inside the Titan M using a key encryption key that is generated from several internal elements. Now, these key blobs are then stored, encrypted, in the Android file system. So whenever an application wants to use a key from Strongbox, it asks the system to send the key blob to the chip. The chip will decrypt the key blob and use the key to perform the operation. So it's interesting to note that as long as the root user can, as long as the user, so root can access all the key blobs that are present in Android file system, so it can use any key, but it should never be able to extract the keys. Now, something that would be interesting for us to do would be to leak the several elements that are used to derive these key encryption keys. But in short, there is one element that is stored in a memory region that cannot be read from the OS. So it's not the way to go to leak Strongbox keys. Instead, let's have a look to the commands that are used to actually use these key blobs and to perform crypto operations. So the first command, and the one that is interesting for us right now, is begin operation. It contains the key blob and the characteristics of the key, meaning the algorithm, the key size, and information like this. And whenever the chip receives it, it will decrypt the key blob and then save the decrypted data somewhere at a fixed address for later. So by now, we should see where we are going. The two other commands are not really interesting for us, but in short, they allow the system, the chip to perform the operation on the data that it contains. So our strategy is simple. First of all, we get the key blob from the device. They are stored in a database inside the key store directory, at least starting from Android 12. Then we forge a begin operation request with it. We send it to the chip will decrypt it, and then we use our vulnerability to leak this decrypted key from the chip memory. So now time for a live demo. And I will call Damiano to help me with this. So here you should see our demo application running on the Pixel 3a device that runs the vulnerable version. So let me just first. Okay. So whenever Damiano enters a secret in this application, the application will generate a Strongbox key and then encrypt it with it. So it will then print the ciphertext, as you can see, both on the screen and on the log. So we have the IV and the ciphertext. The next thing we do is that we will, before we use our vulnerability, so here the first command I'm using, well, first of all, there is an extra step. I need to stop the citadel daemon because it's kind of locking the communications with the driver, and our tool is will communicate directly with the driver. Here we go. So now I'm using the leak KB command that we implemented, and this command will simply list the key blobs available, so stored in Strongbox from the database. So we see there is only one, the one corresponding to our demo app. So the next thing is that we will leak it. Hopefully it will work. Yeah, so the bytes you see are the bytes of the key, of the AES key that have been used to encrypt this secret. So the next thing is that we will simply convert these values into a format accepted by OpenSSL, because we will use OpenSSL to decrypt this ciphertext. So I will do some copy pasting from my cheat sheet because I don't know the command by heart. Oops. The pipes. Yes. I will just remove the spaces from the key because otherwise OpenSSL won't be happy about it. Okay. So now I'll just give this ciphertext to OpenSSL. Okay, I provide the IV and then the key. Great, so here we go. We decrypted our secret. Thanks. So no need for the video. Okay. So before being able to put in place this attack, there are a few conditions that must be followed. So first of all, we need to be able to talk to the chip. So in our case, we rooted our device, so it's fine. But in the real life, you need other vulnerabilities, of course, to get to that point. And the other thing you can try is to do to interact directly on the hardware level with the SPI bus, like remember the picture I showed at the beginning of this presentation. The next condition is to access the key blob. So here again, you need to have enough privilege to read the database, or you can find a way to bypass the file-based encryption, which may sound even harder. So this is just to highlight that before being able to put in place this attack, there are a few extra steps that must be followed in real life, so other vulnerabilities to be exploited. Now, we wanted to show you this mitigation whenever implementing an application and whenever declaring all the parameters to use a strongbox key. It's possible to add this, this flag that we highlighted, set user authentication required. And when set to true, the key blob will be encrypted a second time with the value derived from the user password. So whenever the application will try to use this key blob, the user will be asked to enter its password. And of course, the best mitigation is to update the firmware, since we reported this vulnerability to Google and it's now fixed. So now it's time for a conclusion and with some takeaways. So first of all, the Titan M is an interesting target, especially because it's very important for the whole system security. We show that with black box fuzzing, you can easily get the surface bugs, but emulation-based fuzzing is really more effective on such targets, even though there are a few tricks that you need to put in place to optimize the results. We discovered this critical zero-day we presented, and it allowed us to execute code on the chip and to leak pretty much anything from the chip's memory. So we used that vulnerability to it was enough to leak strongbox keys, like any strongbox keys that were stored on the device. The last thing is that we would like to thank Google for handling our vulnerability reports and for making the efforts to fix everything before today so that we can disclose the vulnerability for you. So this is the end of this presentation. You can find here a link. We will push all the materials of this talk in our GitHub repository, so you have the link here. And thank you everyone for listening.